Okay, so I will start first with maybe the normal stress and shear stress, and then we go to the next part, okay? So maybe I will just go to the previous slide. Okay. So actually in our course we have two type of stresses, normal stress and shear stress. The normal stress is sigma, shear stress is tau. So I will start sharing my screen. Sorry, sharing my like whiteboard screen. So hopefully I can see my whiteboard now. So the topic today, or the first topic today, is stresses. So actually we have two types of stress. The first type of stress is the normal stress, and we can give it the symbol sigma. Normal stress means we have, like for example, this cylinder or this element, and the normal stress like is a result of like applying force, and the relation of this force on the cross section. This is the cross section of this member or this rod. So actually the cross section is, for example, a circle. So if I ask you what is the relation between the force, the applied force, and the cross section, do you know? Anyone know?
No, I don't.
Oh, sorry,
So it is parallel or normal to the force to the cross section.
Parallel?
No, it is normal to the section or perpendicular to the section. So actually, if this our section, if we simplify it as horizontal line, so the force is perpendicular or normal or perpendicular or parallel perpendicular. So actually, if the force is perpendicular to the cross section like this one, so we consider this as normal force. So normal force mean force perpendicular or normal to the cross section. If the force is normal or perpendicular to the cross section, so this means it will cause normal stress.
Right. The other one is shear.
Sorry? Yep.
The other one is shear, which is parallel.
Yeah. So parallel is shear and normal is normal stress. So actually the normal force, we will give it a symbol N, and the normal stress, we will give it the symbol sigma. So now what is the relation between stress and force? I think you have learned about this before in the footing design. The relation is any stress equal to the force over the area. So the force in this case is N, the area in this case is A. So what is the formula for normal stress? Sigma equal to N divided by A. So this is the formula you need to understand, where N is the normal force and A is what? The cross-sectional area. Okay? Do you understand this part? So if we do a quick example here, if we have this is our like cylinder, the cylinder has a diameter of, for example, d equal to 200 millimeter, and we have a normal force applied. How I know it is a normal force? Do you know?
Because it's perpendicular.
Yeah, because this is the cross section and the force is perpendicular, so this is a normal force. So in this example, I give you the force as 10 kilonewton and the diameter is 200 millimeter. And the question is, can you find the normal stress? First of all, I give you a hint, it is a normal stress, but in the exam or the quiz, you will need to find it. So this is normal stress, right? Again, because the force is perpendicular to the cross section or the section. Right? So can any of you help me to find sigma? So sigma equal to N divided by A. We know N as 10 kilonewton. The problem now is how to find A. What is the cross-section area here? Is it square or circle or rectangular?
That's like way back in the notes.
Sorry?
Sorry, just going through my notes.
Notes?
Uh, two-
Yeah, it is similar to the one before we did. So it is circular section. So circular section, I will give you the area now, but the main thing is the cross section of this is an area of a circular or a circle. So the diameter is 200 millimeter. One hint to know it is circle. If he give you diameter, so it cannot be a square or a rectangle. Okay. So the first step is we need to find how much is the area. So area is equal to pi d squared divided by 4. Okay, so this is the area of circular section. So pi times the diameter squared divided by 4. Yeah, which is similar to what Karen said, pi r squared. So what is the difference between this one and this one? Both are the same, but for this one, if we have the radius, this one if we have diameter. Okay, so usually if they give you the diameter is from here to here. Okay, so this is the diameter. What is the radius? This is the radius. From the center to the edge is the radius. Okay, so both are okay. Don't worry about that. Okay, so now what is the area? Pi times 200 squared divided by 4, which give us a value of 31,415.93 millimeter square. This, if it is rounded up to two decimal places. So this is the area. Now the last step is to find sigma. So sigma equal to N divided by A. A already 31415.93. N is 10. So here is a small trick. The area is in millimeter squared, and usually in stresses, the unit should be Newton and millimeter. Okay, so if this is kilonewton, so we need to convert from kilonewton to Newton. Do you know how to convert from kilonewton to Newton?
10 would be 10,000.
Yep. So to convert from kilonewton to Newton, K means 1000. So we need to multiply by 1000. So to convert from kilonewton to Newton, you need to multiply by 1000. Okay. So if we multiply this by 1000, so it become Newton. So now the final answer will be, or the stress will be 10,000 divided by 31415.93. So it become 0.318. To two decimal places, it become 32. What is the unit for this one? For this stress? If you look to the units,
Newton per millimeter square.
yeah, so add the numerator, it is Newton, denominator is millimeter square. So the unit for stress should be Newton divided by millimeter squared. Or do you know what is equivalent to Newton by millimeter squared?
Not kPa, is it?
Yeah, but it is something like kBA, but it will be MBA. So kBA kilopascal, MBA megapascal. So actually we can replace this, or you can use both of them, MBA or Newton per millimeter squared. Okay?
Yeah. And you mentioned before that in the exam we're gonna have to find uh the stress, normal stress, before we can work out the rest. Is that what you said?
For what? You need to find the stress if it is required. So if the stress required here, so you need to know the normal force and the area. So I worked out the area first, and then using the normal force, I found the stress. Is that what you mean?
I think so, I guess, because you said before that you'll give us the stress now, but in the exam we're gonna have to find the stress ourselves. So is that what you just
No, no, yeah, you mean here. I mean the type of stress. So for example, if the question asks you what is the type of stress, so you will say it is normal stress. This is what I mean, not the value itself.
we'll have to work out whether it's normal or
No, no, you just say it. So you need to be understood, not proven. Like for example, it is when you see this diagram here. So what is the type of stress applied?
normal or the other one. Yep.
Yeah,
Shear.
normal or shear. So you decide or you select. Okay. Then if we ask you what is the value of it, so because I give you directly the stress is sigma. So sigma is what normal stress. So it is like a hint to find it. Okay. So do you understand the normal stress?
Yep.
Okay. If we go back to the slide, we have another type of stress, which is shear stress. Shear stress, we give it the symbol tau. So sigma for normal and tau for shear stress. So for example, if we have something like this, just to change the circle, and here the force in this case is in this direction. So we have this force, we call it V in this case, and the cross section in this case is this is our cross section. So if I ask you what is the relation between the cross section and the force, is it parallel or perpendicular?
This time.
Yep, parallel. So shear stress is due to shear force, we can call it V, which is parallel to the cross section. So if the force is parallel to the cross section, or in other words, it is in the same plane of the cross section, so this means it is a shear force. The shear force will cause shear stress or tau. The formula for tau, can you expect the formula of tau? Any stress?
Force over area.
Yeah, so still force over area. What is the force now in this case? V. What is the area? Still A. So actually the concept is the same, but what is the difference? The direction of the force. So the shear stress is equal to the shear force divided by the area. Okay? So if we know shear force and area, we can know tau. So if we have a short example here as well, if we have same force, what was the force in the previous example? 10 kilonewton. And I will keep the area almost the same. So if we have a square, 200 by 200. So what is the cross section in this case? Do you know? Square or what? Square. So square 200 millimeter by 200 millimeter.
Yeah.
Okay. So if I ask you, what is the stress type first?
Yeah.
Second is how much is the stress? So this one to explain what I meant in the previous example. So what is the answer for the first question, guys? Do you notice the stress type in this case? We have only two to select from. What are the two?
Shear.
Shear or normal. In this case, it will be shear stress. Why it is shear stress? Because, yeah, the force is parallel to the cross section. Is that correct?
Perpendicular to the cross section. Ah, sorry, yes, parallel to the cross section.
Yeah, parallel to the cross section. So this is the first part of the question. Second part, how can we find the stress? Now the stress is tau. Tau is equal to V divided by A. How much is V in this case? 10 kilonewton. How much is A? We need to find A. In this case is A for a square. This one is easy for you. What is the area of a square?
Good.
The product of the two dimensions. So L times L or L squared. So what is L? 200 square, which is 4,000 millimeter square. Is that correct? Are you okay with that? Okay, so now we have 4 millimeter. So can we use the 10 kilonewton like that, or we need to convert it to Newton?
Well,
How we convert to Newton? We multiply by what? 1,000, right? So this become 10,000 divided by 40,000. So it is 0.25. What is the unit?
Newton per millimeter square.
Newton
Just
per
megapascal.
millimeter squared or megapascal. Okay, so the final answer here is 0.25. The final answer is the previous one was 0.325. 0.32, sorry. Okay. Do you have any question, guys, for this two type of stresses?
So when we're working through the normal stress, depend what dimensions they're giving us. If it's Santi, if they're giving us diameter or radius, is how we're working through the area, right?
Yeah, the
Going back
dimension.
to,
Yeah, the
going back to the
dimension
previous.
given. You mean here? You mean here?
Yeah, so it's depend of dimension they're giving us. Is a diameter or radius? Is which equation we're using to get the area.
Yeah, both are okay, but I will just clarify something for you. So, do you know what is the relation between D and R? D is what? Diameter. What is
And
R? Radius.
radius.
What is the relation? Diameter is 2 times the radius. So if you look here, so if this radius, so diameter is 2 times the radius. Okay? So actually, it's up to you to use this formula for area by d squared divided by 4 or by r squared because they are both identical equation, not different. But usually in our course, we give you the diameter. So you can, if you want to memorize one equation only, so you can use this one. What is the other option? If he give you the diameter, so how much is r? R is d divided by 2. So for example, if I give you the diameter as 400 millimeter, so what is the radius equal to? 200. Okay. Do you have any other question, guys? So all good with the stress?
There was some examples provided in that week 6, which obviously I'll go through after this session. But is there any other ones you could provide, I guess, as an exercise for us, or maybe we can.
Yeah, I can. If you want more solved or unsolved example.
I know, like how we have the quizzes within the weeks. So there was a question proposed and then a solution. So I guess we just go through that and then work through tonight's material to hopefully get the answer in the test.
Yep. If you want more question to practice, I can share with you. But I think just try to focus on what you have because you have a lot of like topics or a lot of calculation to practice, not only this one. If the focus only on normal and shear stress, I can give you more, but actually the quiz is covering a lot of other things as well.
We also need to do calculations about the shear forces and bending moment, right? And
Yes,
this week 6.
this is what I will go through now.
Thanks.
And actually, the part I did now is part of week 6. I think this is the first part of week 6, right?
Yeah, correct.
Yeah. So second part of week 6 is the bending moment and shear force diagram, which is also one of the important parts in the course and in the quiz. Okay. Have you gone through these parts before, like shear force and bending moment on beams?
Yeah, briefly, I guess, in structures 1.
Yep. So what you remember from structure ones? Do you remember what is the like what is the practice you have done? Or I know it's lecture one you have the trusses and the spaghetti test and so on.
That was, yeah, the spaghetti bridge.
Yep. Okay. Anyway, so I just want to share with you the important parts. So the first part is we need to know how to calculate and draw the shear force and bending moment diagram on two types of beam. Okay. The first type of beam is beam. First of all, it's called simply supported beams. I will let you know why now. And the first one is subject to point load. So the first case we have is beam subjected to point load. What does this mean? We have a beam. Simply supported means one support is roller and one support is hinge. This is the simply supported beam. Okay. This beam has span. The span we call it L. So L is the span or the length of the beam. Okay. Have you seen this beam before?
Yes.
Yes. Okay. So the case we have, if we have a load, point load at one point in the middle, we will give it symbol B. So if we have point A and point B and point C, so we need to know how to find shear force and bending moment on this beam. Have you go through this part in the slides or the videos or not yet?
Yes, I guess when he moves the kilonewtons from point A to point B.
B. So we have A, B, C, right? What is the first thing you need to know? The reaction. So I will give you as a step. So step one, we need to find reactions. Do you know how we can find the reactions here? I think you can remember this from structure one. Because in structure one, you mainly do what? Structure analysis for trusses. So how many reaction we have for this case, if you know?
Clockwise and anti-clockwise.
Sorry, I didn't hear you.
So two reactions,
Yep.
anti-clockwise.
So we have two reactions at A. Why? Because A is a pin support and C is a roller support. So for the pin supports, we have two reaction. One is vertical. We can call it YA or AY. And we have what as well? XA. For C, we have YC. So how many reactions in total? Three reactions, right? Do you know how to find the reactions for this one?
Yeah, there was a horizontal reaction acting upon the vertical and then going over to the C point, which equals 0, and then going up or something like that. That was in the video.
Yeah, but yeah, in the so you understand how I assume the reaction first?
Yes, that's right.
So why this one has two? Anyone can tell me why this has two and this has one only? So for pin support, for the pin support, we have two reactions, which is X and Y. For C, C is a roller. So if it is a roller, so we have only one reaction, okay? Because the roller is allowing the member or the support to move, so it doesn't have a horizontal reaction. But for the pin, it has two reactions. So the total number of reaction is three reactions, okay? Now the second step, how to find, or the same step, how to find this reaction. What is the value of XA, YA, and YC? Do you know? Actually, we have three equilibrium equations, summation fx equal to 0, summation fy equal to 0, summation the moment at any point equal to 0. Okay?
Static equilibrium.
So we have horizontal forces, vertical forces, and moment. Okay, I don't want to go very deep in this one, but to simplify it for you, because I know maybe this might be too much for you now. So do we have any x forces here? Any x forces rather than the reaction? What do you think?
Just that one.
Yeah, so just that one. So this means this one should be xa should be 0. So if we apply summation fx equal to 0, so we have only one force xa, so xa should be equal to 0. For the other reactions, ya and yb, or sorry, ya and yc, so because the force in the middle, so b is in the middle, so actually this force will go or will be distributed between the two supports. So what you expect, how much of the force will go left, how much of the force will go right?
Action has an equal reaction.
Yeah, because it is in the middle, so the reactions will be equal, right? That's good. So we can just simplify the reaction for us. So actually, YA will be equal to YC equal to what? B over 2. So what I want you to memorize or to understand, if we have a case like this, so what is the case we have? We have one force in the middle. So if we have one force in the middle, so the two reaction actually will be equal and will be half of the force on the left, half of the force on the right. Okay? So this will simplify the reaction and we can write down the beam again or draw the beam again. So this is our beam and the reactions are, if this B, so the reaction are 0 and B over 2 and B over 2. So if I ask you now, this is A, B, and C. What is the reaction for this type of beams? Half of the load on the left, half of the load on the right, and the horizontal reaction is 0. Is that okay? Now, the next step will be how to find the shear on each part of the beam, or how to draw the shear force diagram and the bending moment diagram. So we need to know how to draw the shear force diagram, and we call it SFD, and the bending moment diagram, or BMD. So this is an important part of the like the question, or this is an important part of what we need to know today. So I will start with the shear first. So if I have force B and I need now to like you remember or recognize what we have say at the beginning of our session. So if I want to draw the shear force diagram, what does the shear force mean, guys? Force parallel or perpendicular to the cross section? Do you remember?
No.
Yeah, so force parallel to the cross section. So actually the idea is to draw the shear force diagram. We need to make some cuts in our beam or some cross section. So we will not draw for each point of the beam, but we will have one section at the start of the beam, one section before the load, another section after the load, and one section at the end. So we need to find the shear at these four cuts. And then we will need to draw some guidelines like this. The guidelines are actually at the cuts. Then we will draw a datum. This datum is parallel to the beam itself. So if the beam horizontal, so this is horizontal. So I will draw the shear force diagram on this line. Okay. So the first thing you mention is any shear force means the force parallel to the cut. So if I ask you, what are the forces that cause shear on this beam? Do you know what are the forces that cause shear? So our cuts are vertical. So what are the force parallel to the cuts? All the forces we have B2 and B and B2. So these three forces are causing what on our beam? Shear. So this shear, shear, and shear. I will ask you another question to make sure you understand what I mean. Is there any force here that cause normal force on the section or the cross section? Do you know?
Zero.
Be at the point.
Zero? Yeah, but what is the force that are perpendicular to the section? Thank you, Kishobong, and who else? Sorry, who said zero again?
Me was me.
Okay,
Matthias.
Matthias. So thank you, Matthias, and thank you, Kishobong. So what is the forces that are perpendicular to the section I made or the cuts I made? This one here, in highlighted in pink. This one here. So if we have X forces, so it will cause normal. But we don't have in this case, so we don't have any normal force on this beam now. Okay? So the first thing you need to know is the reaction and the applied loads are causing what on our beam? Shear. Now how can we draw the shear force diagram? Anyone know, or anyone can give me a hint how to start?
So that force over area.
No, we are not calculating the shear stress.
Sorry.
We need to know the shear force now.
Oh, so M equals F times D.
This is the moment. We need the shear.
I'll be quiet then.
No worries. I just want you to think. So if this our cut, what are the forces that causing shear? The force that are parallel to the cut, right? So now the idea is we can't deal with the beam as whole at once. So what we have done is making cuts. If you look to any cut is dividing the beam to two parts. One part from the left and one part from the right. Okay? Which one is easier to study as the first cut, number one? Left or right?
Left.
Left, because left we have fewer forces, right? So if I ask you, what are the forces that cause shear from the left? Do you know? Here is the left again. So to the left of cut number one, we have, if this cut number one, quickly, we have from the left, we have one force here, which is B over 2. So what is the shear at cut number one? This force here. Okay. So that's why I will go from the 0 here and go up b over 2. That's is the shear here. So here the shear at A is or at 1 is actually the reaction. So the reaction is the shear here. So how I did it again, I make a cut at 1, then I take the forces to the left of the cut. So I found that only B over 2 is the only force that causing shear from the left. You will ask me why I go up, because from the left, if the force is going up, we go up. So the force is going up or down, B over 2. What do you think? This force is going up or down?
Gonna go down.
Just going down or up? The arrow is going up or down?
It's going up, up.
Going up. So that's why if we call this a datum, this line is the datum line. So I start from 0 and go up. Okay? Again, I go up because the reaction is going up. Do you understand this point?
I thought you were talking about point 2.
No, I still at point 1. Okay, do you have any problem at 1? Okay, now from 1 to 2, how can we draw the shear from 1 to 2? Do you have any idea?
So we go across to 2 and we go downward. Right?
No, again we do the same concept. If I make a cut at 2, what is the idea of this cut just before the load? Because if you look to the left side of the cut, what are the forces in the left side of the cut? Is there any additional force from 1 to 2? No. So if it is no, this means the shear will stay same values from 1 to 2. Okay? So the idea is I make cut at 1 and draw the shear at 1. Then from 1 to 2, no loads. If no loads, so the shear will stay as a horizontal line, or the value here equal to the value here. Does this make sense?
Yes.
Okay. So this section 1 and section 2. Now section 3. If I ask you the cut at 3, what is the additional force at cut number 3?
Down.
Yep. So from 2, this is the idea of 2 cuts at same point. So 1 cut before the loop, 1 cut after the loop. So from 2 to 3, what we have added? Force B down. So we are at B over 2. We need to go down. How much down? B. So if we go B down, so this means we have B over 2 above the datum and B over 2 below the datum. So how much is the total drop here? Do you know? B. Is this okay? So I was at B over 2 at the top, then I drop B. So this all together is B. Does this make sense?
So it's equal.
What?
Equal.
Equal? What does mean by equal here? You
So
mean both are equal? Yes, because B over 2 are above and B over 2 below. So equal. Yes. Is this what you mean?
yes.
Okay. So you understand the concept? You understand what I am doing, like step by step?
Kind of, yeah. Keep going.
Okay. I will like test that with this part. What happened between 3 and 4, guys?
No load.
No load. What does this mean?
There's
Horizontal line to the right.
Horizontal line. So why horizontal line?
Now go up.
Yeah, because no load between 3 and 4, right? So actually the value will stay b over 2, similar to here b over 2. And then after section number 4, if we look at it from the right hand side, or if we continue from the right hand side, how many forces from the right hand side? One force. So from b over 2 we go up until we reach what? 0. So the idea is you start at 0, end at 0. Okay? And this is above the datum, so we give it positive, and this is below the datum, so it is negative. Okay? So the sign convention for shear, above the datum positive, below the datum is negative.
That a static equilibrium.
Yep. So this means it is under equilibrium, because otherwise, for example, if I start from 0 here, and don't end at 0 here, this means our reaction is incorrect. So what is the check you can do to make sure your action is correct? You start at 0 and you end at 0. Okay? Do you understand the shear force diagram now?
I think so. In the exam, will we be given figures and then we've got to work out whether it's going to be 0 or not? Or
No, you will draw the figure itself. That's why I'll try to explain to you how to draw the figure. The important part is how to draw the figure. Do you understand now how to draw the figure?
no? Yep.
How many if you understand? Matthias, okay?
Yeah, I understand this part. Yes.
Michael, Karin, Kishbong,
Work in progress.
Dibanda, and Nicholas, Van, Tai, are you okay?
I'm still trying to work through this. Could you do another example?
Yep, I will do. But I will, because we have another beam, so I will do in the next beam. This is going to be in the quiz. You want me to give you the quiz, Kishbong? Okay, so this will be in the quiz. Is it good hint, Kishbong? Okay, so now the important part is how to draw the diagram. Do you understand this part for now? Okay, so now I will ask you some question about this. Do you know where is the maximum shear value for this diagram after you draw it? So maximum shear location. Do you know?
2 and 3
What?
in the middle, 2 and 3.
In the middle? Why in the middle? If I color it for you, so we have this part, right? And what else? This part, right? So where is the maximum shear location?
Between 1 and 2,
Yeah, between 1 and 2, or between A and B,
A
right?
and B. Yeah, correct.
Yeah, because all of this has same value of shear, B over 2, right? So you can't just select B or A because all this value is the same, right? Do you understand what I meant here?
Yes. Yeah. Okay. So that's where the maximum is. Yeah.
Yep. So now let's go to another part. which is bending moment diagram. So draw the bending moment diagram. So actually there is two options, but I will just give you the easy option. The easy option is there is a relation between the moment and shear. What is the relation? The moment is the integration of shear. Have you heard about integration before?
Not that I recall. No.
Okay, no worries. So in simple words, the moment is the area of shear. Are you good in areas, or we choose the other way? Are you all Do you know how to calculate the area of a rectangular or not? I think this one is easy for you, right? Okay, so just because we already have done the shear, so this will be much easier for you to understand. So actually we have already the shear as we did. So if this is our beam, so L over 2, L over 2. We have calculated the shear here as B over 2, B over 2, and B over 2, B over 2. This is positive and this is negative. This is our shear force diagram. And the best way to draw the normal force the bending moment diagram is to just continue your guidelines at the same points like that. So this was our cut number 1, cut number 2, cut number 3, and cut number 4. So, and this is our datum for the bending moment diagram. Okay. So the idea is we will calculate the moment at each section as the area of shear at this section. So if I ask you quickly, what is the area? If I cut here, what is the area at this section of shear? Is there any area of shear at this section? Again, our cut is dividing the beam to two parts. One part from the left, one part from the right. So is there any area here?
Would be if there is, including parts 1 and 2.
Sorry, what is the area here? At 1, the area, there is no area because if you cut at the edge, so there is no shear. If I cut here, so I have this whole area, right? So at 1, what is the area at 1?
Okay.
M at 1 is 0 because no area at 1. So actually, just to keep in mind, all the time the moment at the beginning of the beam is 0 because no area at the beginning. Okay? The moment is easier because what is the next cut? 2. If I ask you, what is the area of the shear at 2? If I cut at 2, so this is our area. Do you know how much is this area? So M at 2 equal to the area
L1,
of the
2,
shear at 2, which is equal to what?
L1, 2,
B over 2 multiplied by L
L1,
over 2. Is that correct? So this is the height and or the width, and this is the length of the rectangle. So actually the rectangular is this rectangular B over 2 L over 2, and the sign is positive. Can you find the area of this part? So this dimension multiplied by this dimension. So do you know now what is the area equal to? BL over 4. So the moment at section 2 is BL over 4. Is that okay? Or kind of? Okay.
Yep.
Okay. So now we know the value of the moment. What is the sign of this moment? Positive. So where to put above or below the datum? Actually, it is below. For the moment, they flip the sign. There is a reason, but we don't need to go through this now. So actually, what is the sign convention or what is the sign for the moment? We put the positive below and the negative above the data. So if the moment is positive, we put it below or above the datum below. So the moment here is BL over 4. Are you okay with this value? So the value come from the area of this rectangle. The direction or where I put it based on this. So if it is positive, below the data. If it is negative, so it is above the data. Is that okay? Okay. Thanks, Matthias. So what is the next step, guys? The next step, how to connect between this 0 and this BL over 4. How we connect this point with this point.
Diagonal all the way to the PF4 from 0.
Yeah, so we connect with what? Can you say it again, Matthias?
A diagonal, so you're going diagonal from 0 to PF4.
Yeah, we will go diagonal, but straight line, we have two option, guys, in our course or in our type of beam we will study today. So we go straight line or curve. What do you think?
A straight line because there's no forces in between them.
Yeah, straight line. So thanks, Matthias. So we will connect between these two with a straight line like this. So the important thing you need to know for this type of beam, for the moment will be straight line. So if I ask you, just to clarify this point, why we connect to the straight line, guys? Because we have only point load on this beam. So if we have a point load, how can we connect the bending moment? Straight line. Is it okay? No comment. Okay, so now we continue to the next point. Now we have finished the moment. Can you tell me how or why we finished? Do you know what is the moment at 3? We have the moment at 2. What is the moment at 3? Moment at 2 and 3 are the same.
Same P2
Yeah.
over
Yeah.
L2.
Say it, Matthias. Sorry, I disturbed your. What you want to say?
No, I say the same P over 2 times
Yeah.
L over 2 is the same as
Yeah.
the
So same area, so same moment, right? So actually the moment at 2 and 3 are the same. Now, what is the moment at 4, guys? What you expect? The moment here is 0 as well. So actually, the moment is 0 at these 2 points, and we connect from here to here with another straight line. So actually, how many points we need to calculate the moment at for a point load beam? Only 1 point. Because the moment here all the time will be 0, the moment here all the time will be 0. And what is the sign for this moment, guys? Do you know? Is it positive or negative moment?
positive
Positive. Why it is positive, guys?
because it's below the line, the dotted line.
Yeah, because it is below the datum, and as we mentioned, we put the positive below the datum. So this is a positive bending moment diagram. So now, if we look to these two diagrams, are they easy for you to understand or not after our discussion now?
Getting there,
So better than before the session at least?
definitely.
Okay, that's good. So now if I ask you another question about this moment, where is the maximum moment location, guys?
PL over 4.
Yeah, location, not the value. The value, you know the value. What is the
Yeah.
location? In
In
the
the
middle?
middle, between
Yeah, or point what? P.
Oh, point P, yeah.
Yep.
Going back to the
But I mean, after you draw the bending moment diagram and shear force diagram, you now know where is the maximum location of the shear and bending moment. Is that correct? So that's why we need to draw, or we need to know how to calculate the shear force and bending moment diagrams. Because when we are designing a beam, we look at two important information. What is the maximum moment on this beam? And what is the maximum shear on this beam? Okay, and what is the location of the maximum shear? What is the location of the maximum moment? Okay, do you have any question now for this part? So if we summarize this beam quickly, so if we have a simple beam with a load B in the middle, so how many reaction we have? 3, 0, B over 2. This is what we have done already, right? And B over 2. Is that correct? What is the next part? How the shear force diagram and bending moment diagram all look like together. So for the shear force diagram, we will go up to B over 2, then straight B over 2, then below B over 2, then straight B over 2. This is positive, this is negative. What else? Bending moment diagram. So what is the bending moment diagram here, guys? You know, 0, here 0. The maximum moment is under the load in the middle. What is the value? BL over 4. You connect it together with what? Straight line or curve? Straight line. What is the sign? Positive or negative? Positive. So this is the shear force diagram for a simple beam with a point load, and this is the bending moment diagram for a simple beam with a point load. Okay. Do you have any question, guys, for this one?
So under the bending moments, if we have a curve, that means we don't have any force in any part of the beam besides the left and the right. Is that right or no? For a curve instead of having a straight.
Yeah, all the time, if you have point load, all the moment line will be straight lines.
But in the case we don't have any loop point, that means it's a curve. That's why we have two options in the bending moment.
No, the other option will be with the next beam I will do.
Oh,
Okay, so all the time for if you have this point load,
mm-hmm.
these lines will be
That's right. Yeah.
straight lines. Okay?
Yeah.
And all the time, this will be lines parallel to the datum. As you can see, what is this line? Horizontal. Parallel to what? This one is parallel to this one. This one is parallel to this one. I mean, let's summarize this. All the time, the shear will be rectangulars. Can you see that? Can you notice that? The shear is two rectangular here. The moment is triangle. Okay? What I want you to get out of this session, you memorize this drawing. Can you memorize it, or can you understand how to memorize it?
Yep.
Are you saying something? I can't hear you.
Yeah,
Anyway, what?
I understand. I can memorize it, but yeah, I guess we'll see what happens in the next one when it bends, or not bends, but the
We
curve.
will see the next one, but this is the first case we need to know today. Let's call it case one. So the session will be a little bit long. Are you okay?
Fine.
Do you want to continue or stop at here?
I'm happy to continue.
Okay, that's good. All others are okay? If you want to leave and watch the recording, it's okay. I will continue so that you can go back to it. So our first case was, if you go up here, so simply supported beam subjected to what? Point load. Okay. The second type of beams we will have, or we might have, and you will see in the slides, is, do you know what? Simply
Supported beam.
what?
Please supported beam.
Yep. And what is the type of load?
Point load.
Yeah, we have finished the point load. So subjected to uniformly
L.
distributed load, or UDL. So this is the second type of beam. You need to know how to draw the bending moment and shear force diagram for. So in this case, we have a beam, and the beam is simply supported, means one support is pin and one support is roller. And actually, the whole beam is under uniform load. Uniform means the load is same value over the length of the beam or the span of the beam. I will call it KW in kilonewton per meter. So this is our length or our beam span, L. So this is point A, this is point B. So now if we want to do the same as we have done just now for the first beam. So what is the first step if you remember from the previous one? We need to find the reactions. Can anyone guess what are the reactions or how many reactions first we have here?
So pin go up and right,
So we have two
and roller
reactions.
go up and down. Yeah.
Yeah, so we
And then
have
roller is only
XA,
one reaction.
yeah, YA, and here we have YB, right? So how many reactions in total? Again, three unknown reactions. That's right. So now how can we find the reaction? Similar to before, what we have done before for XA, we don't have any other horizontal force, so XA should be 0. How about YA and YB? Any idea or any guess? Zero. So Kishbong said 0 for the reaction. Can the reaction be 0, guys?
Not for Y. YA and YB can be
Yeah, because we have already loot. So if Y is 0, so why you are not, why you are here today? So this is impossible, Kishbong. So we have applied load downwards, so we should have reaction. So there is a small trick here. What is the small trick? We can't actually deal directly with W as uniformly distributed load. So we need to simplify. Yes, that's good, Kishbong. So we need actually to concentrate the uniform load to be able to deal with. So do you know how to concentrate this load? If it is W and distributed over a length L. So do you know how much is the total load? The total load will be W times L. So we have W L as the equivalent buoyant load. So we will just consider that we have a WL equivalent buoyant load. Where this buoyant load will be located, or where it should be located, I'd expect in the middle. So actually, this should be in the middle. So if L over 2, the other one also is L over 2. So now, can you find the reaction? XA equal to 0, YA equal to YB, similar concept to before, WL over 2. So does this make sense with you or for you? So half to the left and half to the right. Okay?
Yep, makes sense.
Okay. So what is the difference in the interpretation of this two problem? Here we have directly the load in the middle. So half go right, half go left. Here the load is distributed. So firstly, to be able to deal with, we just concentrate it first by multiplying the uniform load times the distance or the span. So we got the equivalent load. Because we cannot deal with the uniform load directly, so we need to convert it to equivalent load. So the first step, we got the reaction. So now we have this is our beam. We have uniform load W kilonewton per meter, and this W we have concentrated the load, just a virtual or equivalent load W times L. This is in the middle, so L over 2, L over 2, and the total is L. So the reaction as we got them are 0 here, and we have WL over 2 here, and we have WL over 2 here. So does this make sense with you up to now? So now we need to start next step to draw the shear force diagram. How can we draw the shear force diagram similar to before? We will need to create some cuts. Our cut here will be at the start here, this cut number 1. And actually we don't need more than 2 cuts. So 1 cut at the beginning, 1 cut at the end. Why we didn't have cut here and cut here, similar to the previous one? Do you know? Do you have any idea, guys? Van, do you have idea? Liji, Lijana, do you have... Is it correct, your name? Liji, Lijana is correct? Or, I mean, I pronounce it correctly?
Wait, Lily. You can call me Lily.
Okay. It's hard to respond to your question and write the name, so...
Okay.
So, how we can start, Lily?
Lily.
Or,
So
I mean, sorry, first, why we don't have, like, cut here and cut here?
because it's uniformly distributed.
Yeah, so we don't actually, this is not the applied load. We just use this to simplify our calculation, but there is no point load acting at this point. Is that correct? So that's why we don't need cut here and cut here. So I just try to link this with the previous example so that you have some idea what we are doing now. So actually we will have 2 cuts here. So Matthias, can you start with the first cut? So we have 1 cut here, 1 cut here, and this is our datum to draw the shear force diagram. So if I ask you, Matthias, what are the shear force acting at section or cut number 1?
0.
The shear force, not the moment.
Oh,
If you
W
look,
over 2.
yeah, WL over 2. So similar to what we have done before, I make a cut and study from left side. So I found this force acting upward or downward? Upward, right? So what I will do is just from 0 go up with the value I got, which is W L over 2. Now, this is the challenge now. From 1 to 2, we have loads or not? We have loads, right? What is the load we have? W distributed or WL as equivalent. So how can we deal with this, guys? So the shear force or V at 1 equal to WL over 2. V at 2 will be WL over 2. What is the added forces between cut number 1 and cut number 2, guys? Do you have idea? What happened from or between 1 and 2? What are the forces we have added? This force. Okay? So do you have idea what to do to find V2?
W square over 8.
Not this one. Not this is the moment.
Oh,
So what is the shear at 1? WL over 2. Is that correct?
yeah.
Between 1 and 2, we drop down WL. So actually the shear at 2 will be WL over 2 minus WL. So V at 2 will be negative WL over 2. So actually the shear at the other end will be the same value but going down, WL over 2. So at 1 or at section number 1, we go upward WL over 2. from 1 to 2, we have drop the value of WL. So WL over 2 minus WL, we go to negative WL. And as we mentioned in the previous example, above the datum is positive, below the datum is negative for shear force diagram. Okay? Does this make sense for you now? What are the Kishbonga, have you done this? Can you remove this Kishbong? You don't know how to remove it? You have ruined it for me. Okay, guys, can you see what Kishbong has done?
Yeah, we
Oh,
can see.
Yeah, it's gone.
thank you, Kishbong. You give me a star and then you just give me a 0. Thank you, Kishbong. Okay, guys, so now do you understand what I have done up to now? Yes or no?
So kind of, yeah. So it is bending down because we've lost the W or WL.
Yeah, so what I have done, I start at this point, right? I go up the value we have at point A or at cut number 1, which is WL over 2. Now, from 1 to 2, I don't have any cuts. So what I have done is at cut number 2, I was at WL over 2, and then I drop WL, so I will reach negative WL over 2. Negative means below the data. Okay? So now what is the next step, guys? Do you have idea? What will be the next step?
Will be a straight line from W positive up to minus W over 2
Yes.
negative.
So we connect them
This
with a
is nodal
straight.
points, is nodal forces in between.
Yeah, so the main thing is at the middle should be what? 0. So we connect with the 2 point with a straight line. This part is above the datum, so it is positive. This part is below the datum, so it is negative. Okay, so we have 2 triangles for the shear force diagram. One of them above the datum in yellow. The other one is below the datum in green. Okay, so if I ask you now, where is the maximum shear location?
W over 2 positive.
Yeah, this is the value. Where?
1 at the first cut.
Yeah, at cut number 1 or at point A.
Yeah.
Okay, so do you understand now the difference between the uniform load and the concentrated load? So for the concentrated load, it is 2 rectangulars. For distributed load, what we have now? 2 triangles.
Will change.
Yeah. So these 2 cases, I want you to memorize and I want you to understand. This is the main thing you need to understand. Okay, what is the last step or what is the last thing we need to go to find now, guys? Bending moment diagram. So how can we find the bending moment diagram for this part. If I ask you to do the same thing as we did before, so we have cut number 1 and cut number 2.
So we
Here's
go
the cuts.
down on the first cut. We're going down because it's positive.
Yeah, for the first cut, we don't have any area, right? So how much is the moment at the first cut?
W/2. But
We are the moment now, Matthias. So
oh,
we are in the moment. So for the shear, it's already WL/2. For the moment at the two ends, I memorize this part. Moment at ends are all the time equal to what? 0. So all the time, these 2 points A and B will be 0. The maximum moment will be in the middle. Do you know what is the maximum moment value? WL squared over 8. And it will be positive. Positive means below the datum or above the datum for the moment below the datum. So if you tell me I can't memorize this or I want to know how can we find this value. Any one of you can give me idea how can we find the moment at this point? So similar to what I have done in the previous step, the moment at this point will be the area of this part. So the moment at mid-span equal to area of triangle. Do you know what is the area of a triangle, guys? Of the yellow triangle? Anyone know? What is this span equal to? Any idea? This is half of the beam span, so it is L/2. So the area of the triangle will be half BH. B is the base, H is the height of the triangle. So it will be half times L/2 times WL/2. So can you find out the value, guys? Any of you? Can you work out this one? So for the numerator, we have L, so L square, and we have what? W. So it will be WL squared. We have 2, 2, 2, so it become 8. So do you understand where this value come from? Yes or no?
Where did you get 1/2?
What?
Where did you get 1/2?
What you mean by 1/2?
So in the formula, you've got 1/2 BH.
You mean where this come from? Where this half come from?
That's half.
Yeah. You don't know, or you don't know what is this?
Oh, no.
You don't know. So do you know what is the area of triangle equal to? I will write it down here. So if you have a triangle, so we have B, the base, for example, and H is the height, for example. So if I ask you what is the area of this triangle? So what is the area of a triangle? It is 0.5 or half times the base B times H. Because B times H are what, guys? What is B times H? B times H is the area of the complete rectangular, right? But actually, this part is not existing. That's why we're taking only half of it. Do you understand now where this come from?
You-
Yes?
Thank you.
Okay. Thank you. So, are you okay now, guys? Are you okay with the value? So you understand what you need to know is the value. I just try to give you some idea how or where this come from, but actually you don't need to know that, or you will not be asked. You will not be asked how we can derive this value. So if you can memorize the value, it's okay. So what is the value again? W L squared divided by 8. This value come from the area of shear triangle. Okay. Now, what is the last step, guys? How to connect these points. So we have point 1 and point 2 and point 3. Do you know how to connect these three? Curve. Why we connect with curve? So actually, I will connect this with a parabola or curve. And I just will do something. So if I connect with a line, this is the line. I just try to show that it is not a line. So, and actually,
Bending moment, right?
yep. So this is the diagram for bending moment. So this is a positive bending moment, and this is a parabolic second degree parabola or a curve. Okay. So now, as you can see, this is the bending moment diagram. For a uniformly distributed beam. So this shape is different from the previous shape for the simply the concentrated or the point load. Is that correct? So here we have a parabolic and the value is WL square divided by 8. So now you understand both, or you have a question, guys. I will just draw it final time to compare so that if you keep this slide in mind or memorize it or just refer to it when you go back to it when you need, so it will help you to find the moment and the bending moment diagram and shear force diagram for this type of beams. So this is the two beams we need to know and we work it out today together. So the reaction are 0 and B over 2 and B over 2, right? Here's the reaction because we have WL here in the middle. So we have WL over 2 and WL over 2. So we have some cuts here. Do you remember the cut? The cuts? Here and here. So we have cut number 1, cut number 2, cut number 3, cut number 4. And we have this diagram for shear force diagram. This diagram is for shear force diagram here. And this cut number 1, cut number 2. This for bending moment diagram. And this for bending moment diagram. So we found that the shear here will be the reaction, which is B over 2 and go straight. B over 2, go down. B over 2 and B over 2 and 0. So we have positive and negative. Here the shear is going up to WL over 2, W L over 2, and we connect it with a straight line, so positive and negative. For the bending moment, as you remember, we have 0 here and BL over 4 here and 0 here. We connect them with a straight line, and this is a positive. Here 0, here 0, in the middle. How much is the value in the middle, guys? W, L squared by 8, and we connect it with a parabola and positive. So this is a positive shear, and this is a negative shear, and we have the bending moment here and bending moment here. Okay, so this is the point load, case number 1, and we have here uniformly distributed load, or case number 2. Okay, and that's it for the shear force and bending moment diagrams.
Cool. Good luck to us.
Easy or not?
It is much better now than when I was going through the material a couple of days ago. My head was spinning. But thank you.
Okay, that's good. Thank you. So just need more practice, and that's it.
Thanks, Ahmed.
Thank you, Van. You understand now, Van, or you need more explanation?
I'll most likely have to review the recording again.
Yep. You just need to just try it by yourself and work it out yourself, so that you will find it easy.
Yep. Thank you.
Thank you, Van.
Just like anything, hey?
Sorry, I couldn't hear you, Lily.
I just said practice like anything.
Yeah, you just need to practice, and I think today we have covered huge or a big chunk of the content you need to memorize or revise before the quiz.
Really good. Thank you so much.
Thank you. All other guys, are you okay? No question, or do you have anything else you need help with? Thanks, Dipandra.
Thank you so much for tonight. Really appreciate it.
Thanks, Matthias. And Michael, are you? I think Michael doesn't.
Yeah, no, all good. The more you were doing it, the more it made sense. So I think a bit more practice and we should be all right. Thank you very much.
Thanks, Michael. Good luck, guys. And if you need any other help, just send it through to the course email. And sorry, guys, I was not rostered to respond to the queries last week, but I had to respond to them anyway. Okay, it was not my roster last week. But anyway, if you have any question, just send it this week, and I will be able to respond to them.
Yeah, mate. Very
Thank
helpful.
you.
Yeah,
Okay.
thank you. Thank you
Thank
very
you,
much.
guys.
Thank you.
Good luck, and have a good night, and see you later.
Thank you. You too.
Thank you. Bye.
Yeah, thank you. Bye.
Thanks, Mike.